Good evening everyone. Today we will start with mass spectrometry. As the name suggests, over here we will be looking into the change in the masses, and basically we will be looking into the molecular mass, or we will be estimating the molecular mass of the molecules. Okay. So what is the basic principle over here? The basic principle is that suppose you have a molecule A, okay, so it is passed through an ionization chamber, okay, and in the ionization chamber you have electrons which are used to bombard the molecule, okay, and in this case it is A. So what happens if you are bombarding a molecule A with the electrons? What happens is that the electrons from the molecule, they maybe strike off from their orbitals, okay. So when the electrons, they are getting striked off from the orbitals, so this A, what it becomes? It becomes electron deficient, okay, and it becomes a basically a cation, okay. Now this A, after the ionization, after it passes through the ionization chamber, it becomes A plus, and then over there you have a chamber where the acceleration of this ion takes place. So this A, it is then A plus, it is then accelerated. Now how this acceleration takes place? The acceleration takes place, suppose if this is a cation. So before this ionization chamber, while it is having this ionization, so what we will be having? We will be having a positive electrode, okay. So what it will do? It will repel A plus ions, okay, and then we will be having negatively charged electrodes. In fact, a set of electrodes, there will be two electrodes, electrode 1, say E1, and E2. So the potential of E2 is greater than the potential of the E1. So what it does, since it is negatively charged, it will be attracting these cations through it. However, in between we have a slit, so these cations, they will be moving out of this slit. However, since we are having these negatively charged electrodes, what they will do? They will be attracting them towards themselves, and there will be an increase in the velocity, okay. So these A plus ions, they will be moving out of this accelerated chamber, and it will be coming out with an increased velocity. Now we have an increased velocity of the A plus ions. Then this enters into the analyzer section, okay. Now this analyzer section, it basically, it is having a magnetic field, okay. It is having a magnetic field. Suppose you are getting this analyzer section. Over here you will be having a magnetic field in this region. So what it will do? So up till now, up to this point, your A plus ion, they are moving in a straight line, okay. However, as soon as you are having this magnetic field, this magnetic field Fm, it will create a centrifugal force, or it will induce a centrifugal force onto the cations. Okay, and due to that reason, you will be having a path for the this cations which will be moving in a circular path. Okay, now means at the end of this section you will be having the detector. And this detector, it may be either charged coupled detectors or the CMOS arrays detectors, or in the initial days we used to have the photomultiplier tubes, PMTs. Okay, so this is the basis of this the mass spectrophotometry. Now you would say, sir, how it is how we are able to do this? There are two ways. So what happens over here when we say that we are applying a magnetic field, then it is equal to Fc, which is the force due to the centrifugal movement of the atoms. Okay, so we can write it down as QVB, which is equal to mv square by r. Okay, so this r will be having a hypothetical center over there. We'll be having a hypothetical center over there. Okay, so we'll be having mv square by r. Now we cancel out this v, so we get qb equals to mv by r, and if we take this r is equal to mv divided by qb. So if you see, r is directly proportional to the m by q. Okay, so higher the r, higher should be the mass of the what you call the charged particles. Okay, now in a mass spectrometry, what we have, we have the relative abundance that is the number of charged particles which are reaching the detector. And what is the independent variable? The independent variable is the m by q. Usually we will see whatever the examples we will be taking, for the sake of the simplicity we will consider that q is equal to 1. So our independent axis, it basically it comes out to be m. So we will be getting the mass of the particle, mass of the particle which is reaching the detector. Okay, now in this case, if you see, I have talked about A and it has converted into A plus. Okay, so that means there is no loss of atoms from the molecule. In this case, this ion, it is regarded as molecular ion. Molecular ion. Okay. However, say for example, this molecular ion, this molecule, it breaks into, say, some B plus some fragments, neutral fragments. Sorry. So we will be telling that this B plus, it is a charged fragment. It is a charged fragment. Now this charged fragment, it may be either like this B plus, or it may be B plus radical, maybe. Okay, plus there will be some neutral fragments. Okay, now let us see what I mean by this molecular ion and what I mean by this fragments. Okay, let us take an example where I have CH bond. Now a typical C, it has 6 core electrons. Okay, and apart from this, it will be having 1 electron which it is sharing with the hydrogen, which is also contributing 1 electron. Okay, now when I am bombarding the molecule and it knocks out one of the core electrons, there will be no fragmentation of the molecule and you will be getting molecular ion. However, in the second case, say for example, the electrons, it comes and it strikes off this electron from the carbon side. Okay, so what will happen? We will be getting 2 fragments. The first one is the, say with the C bond, whatever we are getting, so we will be getting C positive, but that molecular fragment will also be electron deficient. Okay, so it will be C plus radical. Okay, carbocation radical. On the other hand, we will be having a neutral molecule, this H plus and this one ions, which is a neutral molecule because it will be having 1 positive and 1 electron of its own. Okay, so it will be a neutral fragment and it will not be affected within the magnetic field. Okay, it will not be affected within the magnetic field. Okay, so this is the first case. So what you are having? You are having this charged particles plus neutral hydrogen atom. On the other hand, if the electron knocks off this hydrogen, this thing, so you will be getting C, okay, and plus we will be getting this H plus cation. So this will be the neutral molecule, neutral fragment. Because this carbon, it is having its own having its own electron. Sorry, over here this one, this will not be the positive one. The positive one will be this one in the second case. Okay, so now this hydrogen atom, it will be affected by this hydrogen cation. It will be affected within the magnetic field. However, this neutral fragment, it will not be affected in the magnetic field. Okay, now let us take an example. Let us take the example of propane. Okay, so what might happen when you are bombarding with the electrons? Say for example, this hydrogen atom, it in the first case, what happens? From the C, 1 core electron goes, so we will be getting the molecular ion CH3, CH2, CH3 plus. So this is a molecular ion. Okay, so if you see the molecular weight, there is no change in the molecular weight. Okay, in the next case, what you can have, this hydrogen atom, it may cut off. So when it is getting cut off, so you will be getting CH3, CH, CH3. Okay, plus. So what is happening now? What is happening now? The molecular mass over here. So if you see 12 multiplied by 3, 36 plus 8 equals to 44. Okay. In this case, what we will be having? It is plus, but where the plus is? The plus is over this carbon. Okay. And what is the molecular mass? 43. In the second case, in the third case, what we can have? This is the first case. This is the second case. In the second case, we can have this methyl group. It is getting removed. So we will be having CH3, CH2 plus. Okay. So we will be having 24 plus 5, 29. Molecular mass will be 29. And lastly, we will be having CH3 plus. This is the third case, and this is the fourth case, and this is 15. Okay. So what we should get in a mass spectrometer, you will be getting M, because if you see in all of this we are having only single charge, so Q is equal to 1. So we can write that our x-axis is M and our y-axis would be the relative abundance. Our x-axis, y-axis is relative abundance. Okay. Now at 44 we will be having some peak. This is 44. Then at 43, if you see, this is a secondary carbocation, and the secondary carbocation, it is having a larger abundance. Okay, so we will be getting a larger abundance over here. So at 43 we will be getting a larger abundance. Okay, because this is a secondary carbocation, and this peak where you have a larger amount of occurrence, or the largest relative abundance, that peak is also regarded as the base peak. Okay. Then third case, at 29 we will be having some peak, and in some cases we will be having 15, 29 and 15, we will be having some information. Okay. Now the CH3 plus group, in many cases you will find that this peak is not present, because this methyl carbocation, it is quite unstable in nature and it is lost within the chamber itself. Okay. However, in some cases you may get a very small peak. Okay. Now suppose we are having another molecule, say butane, and we are having 2-methyl propane, now how would you find out that what is the if I ask you tell me the difference between the mass spectrographs of these two molecules? So where you will be getting, if you see the molecular mass of these two, what it is? 1, 2, 3, 4, 58. This is 58. So in both the cases at 58 you will be getting a peak of the for the molecular ion. Okay, then comes the interesting thing. Suppose we want to move or eliminate one of the methyl group. Okay, so if we want to remove one of this methyl group, so what will happen now? Or you can say if we remove one of these hydrogen atom, what will happen? Or if we want to remove one of these methyl group, what will happen? Say for example, if we want to remove one of the methyl group. Okay, now say when we are removing this methyl group, so we will having 36 plus 3, 5, 7, 43 we are having. Here also we will be having 43, 6, 7 here. So at 43 we will be having the peak. But is there any difference? The relative abundance of the second one, it will be higher because it is we are having a secondary carbocation. So you will be having a relatively small peak over here and you will draw a relatively larger peak over here. So in this way you have to analyze the things. Okay, similarly if you see, if I remove one of the hydrogen atoms from here, it will again be having a secondary carbocation. It is possible. The second one, it will be higher because just few moments back I have told you the secondary carbocations, they are when you are passing the or fragmenting the molecules, you will be getting the fragments where you will be getting a larger number of fragments where the secondary carbocations they are larger. Herein, if you slice off one of the methyl group, so what is happening? You are getting a primary carbocation. However, in whatever way you cut this, you will be getting a secondary carbocation. Okay. Now, since you are getting a secondary carbocation, the relative abundance in the second case, it will be higher, even though both the peaks they will be appearing at 43. Okay. Now, suppose if we want to break down water molecules, so we are having HOH. So in this case, the molecular ion, it is having 18. Okay, then we will be having OH plus 17, and in the case of water, this OH plus, it will be most abundant. Okay, that means they are more stable. This fragment, this charge fragment, it is more stable. Then we will be having at O plus we will be getting one peak, and at 1 we will be getting H plus peak. Okay. Now we have seen how what is the basis of mass spectrometer and how we can analyze the results. Now let's go to the construction of this one. So we have a sample herein, we have a sample holder. Okay, so you will be getting the samples over here, and by certain mechanisms you have to volatilize the sample. And when you are volatilizing the sample over there, where you are having the sample through which you are sending all these molecules, vaporized molecules. These are M double dot. These are the molecular molecules. When you are putting it into the mass spectrometry, so at that region, usually the usually we are having a very large vacuum, and it is in the order of 10 to the power minus 2 torr, or we can say 1 micro torr. Okay, now we are having this. Then I told you that there will be a repelling this thing, so it will be positively charged electrode. Okay, so while these molecules they are getting into this ionization chamber, it will not affect the movement of the molecules because it is not charged, it is just in the gaseous phase. However, as soon as you get into this section where the ionization is taking place, so what is happening? Due to this ionization stuff, these molecules, see, they are entering within a zone where you are continuously bombarding the section with the electrons, and as we get out, we get different fragments. We get carbocations. Okay, we get we get carbocations. We get the fragments which are neutral fragments. These carbocations we get, and then we get this radical cations. Okay, so along with that we get a neutral fragment. Okay, now this is happening. Now once it has become either the carbocation or it has become the radical cations, this positively charged electrode, it comes into the play and it pushes or repels these cations towards the this negatively charged electrodes. Okay, the negatively charged electrodes, where we are having a set of negatively charged electrodes. The potential of the second electrode is higher than the potential of the first electrode. Okay, and they are at the same time they are attracting the cations towards itself, and through this orifice you are getting the cations out of the system, and then they are entering into the this analyzer zone. Okay, now over here, due to the presence of this magnetic field, it is experiencing a centrifugal force, and then it is moving there. Now if you see, if there are heavy ions and if your magnetic field is such that, if you see, there is a variable magnetic field 500 to 8000 Gauss, right? Now when you are having a specific magnetic field B, it is allowing some molecules to pass through. However, if the molecules or the cations they are having higher mass, they are following a larger radius and they go and strike with the column of this analyzer and they are lost. Similarly, if they are having smaller mass, then what will happen? They are going and they are being collected or they are being lost on the other side of the analyzer. Okay, so what we have to do, we have to change this magnetic field such that the cations they gain entry to the detector. Okay, so by playing with this magnetic field, we are basically playing with the radius, which is again directly proportional to the mass of the cations. Okay, mass of the cations. So by changing the magnetic field, we are basically controlling the cations which will be gaining entry to the detector. Okay, so in that way we can find out at what position we will be having what molecular mass. Okay, now the energy of the accelerated electrons, it is 70 electron volts. Okay, so why 17 electron volts? 70 electron volts because as per this de Broglie matter wave equation, we have lambda equals to h by mv. Okay, so we can write it down as h by p. Now the energy, it is given by p square divided by 2 of me. So from here we can write that p, what is p? P is the momentum of the electron. So p is equal to under root of 2 me e. Okay, now if we replace it over here, we get h by under root of 2 me capital E. So our energy is 70 electron volts. So if we put it over here and if we try to calculate the wavelength, it comes out to be 0.14 nanometer. It comes out to be 0.14 nanometer. Now why this is important? Okay, why this is important? This is important because if you see the bond length, between bond length of the molecules in an organic system, this bond length is in the order of 0.14 nanometer. So when there is a match of the this wavelength of this one, of this electron beam, and this molecular bond, there is a breakage of bond. If, say for example, the wavelength of the electron beam, it is either increased or it is decreased, then these electrons, they will pass through these molecular bonds as it is, and they will not induce any breakage or fragmentation. Okay, hence it is to be remembered that the electron gun which is used in mass spectrometry, they generate electrons having an energy of 70 electron volts. Okay, another important thing is that herein, for the sake of simplicity, we have shown that the electron beams, they are moving in linear way. However, in actuality it is not the case. We apply a magnetic field across this beam, and this magnetic through magnets, through permanent magnets, and these magnetic beams, magnetic field, what it does is that it results in the formation of a spiral way. It is moving in a particular direction, but it is spiraling. Okay, now why it is important? This is important because when you are having a spiral pathway, the path length is increasing. Now by increasing the path length, you are increasing the chances of the ionization. Okay, because as I told you, when we are putting the sample into this ionization chamber, what we are doing, the molecules, they are already in the vapor phase. Okay, and when they are in the vapor phase, the chances of interaction of the electron beam with the molecules, it will be quite less. So by increasing the path length of the electron beams, we are increasing the chances of interaction of the electrons with the molecules, so that we get the charged particles. Okay, now I already told you that these carbocations, they will not be having any, they are not radicals, they only have the positive charge, whereas the radical cations, they will be having a positive charge and an unpaired electron. Okay, now this is what I was telling you. So you are having the parent molecules, you are having the these electrons which are coming, and then you can have this non-dissociative result, which is the molecular ion, or dissociative result, where you will be having charged and the neutral fragments. However, in the non-dissociative result, we will be having only the ionized parent molecule. Okay, and then we have, I told you, the repeller. Then we are having this negatively charged electrodes. Okay, usually there are 2 electrodes over here. Then the sample is being put in, and then we are having this 2 magnets, which helps in increasing the path length of the electron beams. Now this is what I have already told you. So however, there are certain things. The sample, you can use a solid sample, you can use a liquid sample, you can use a gaseous sample. However, what happens is that when this sample they enter into the ionization chamber, they have to be in the volatile form or the gaseous form. So if we are trying to analyze the solids and the liquid samples, you have to have a mechanism where you are volatilizing the sample. So if it is a liquid sample, suppose you have a DNA sample. So the DNA sample is there, it is usually present in an aqueous medium. Suppose we are having a DNA sample and it is dissolved in water. So initially we have to evaporate the water, so vaporize the water. After it is being vaporized, and at the same time we have to make sure that the DNA samples they are getting entry into the system, into the ionization system in very tiny parts. Okay, so how it is done? We make it into the form of aerosols. What are aerosols? Aerosols are tiny droplets which are having water molecules. However, before it enters the ionization chamber, the water molecule should be evaporated so that we get smaller or the what you call this dried DNA particles or the genetic materials, and then they are being bombarded with the electron beams, and accordingly we get the electrons which are coming, these charged particles which are coming out of the ionization chamber. Okay. If it is a solid, what we can do? If it is a solid, what we can do? We can use the laser ablation method. In the laser ablation, we have discussed in the atomic emission spectroscopic method. We can immobilize the samples within a matrix, and then we will use a very high power laser to ablate the matrix, which will help in the generation of the very fine particles or fine aerosol particles, and those particles will then be made to enter into the ionization chamber. Okay. So creating of ions. So the ion source is the part of the this mass spectrometer that ionizes the material under the analysis, that is the analyte. So we may go for the electron ionization, or we may go for the chemical ionization. Electron ionization, we use electrons for the ionization process. In chemical ions, we usually use ammonium ions for the ionization purpose. Okay. And they are usually used for the gases and the vapors. Two techniques often used with liquid and solid biological samples. They are electrospray ionization, and matrix assisted laser desorption ionization. In short, it is called Maldi. Okay. Now, in electrospray ionization, okay, first let us see the types of the ionization methods. So first we can have the hard ionization and the soft ionization. In hard ionization, we will be having a very high energy ionization materials, so which impart high quantities of residual energy in the subject molecule, invoking large degrees of fragmentation. So in hard ionization, we will be having large degree of the fragmentation, and resultant ions tend to have lower m by z, because if you are creating larger fragment, then basically you are having lower masses, okay, than the molecular mass. Okay. So example of hard ionization is the electron ionization, EI. Then we have soft ionization, which impart less energy onto the subject molecule, and as a result we have little fragmentations. So over here we have different types of ionization techniques. However, we will only be discussing about the electrospray ionization and Maldi ionization process, because these two are most commonly used in our this biological analysis. Then we can have this inductively coupled plasma. We have already discussed it in the AES, how the ICP method, it can help us in generating the ions. Then we can have this photoionization mass spectrometry. Over here we can use X-ray and or UV to generate the this ions. Okay, and it is a high energy photon either is used to dissociate stable gaseous molecules in a carrier gas of helium or argon. Then ambient ionizations. Over here ions are formed in ion source outside the mass spectrometry. And other ionization techniques, field desorption ionization technique is there, fast atom bombardment is there, you use another atom to bombard the thing. Then we have thermal spray, desorption ionization on silicon. So what happens in some cases, in diodes, what happens is that you have a liquid sample, then you coat and surface, and then you use we use this basically on silicon, this metal or this platform is the silicon platform. Over that you have a thin layer of the molecule which you want to ionize, then you bombard it with other atoms so that you can get the charged molecules. Okay, then we have spark ionization, thermal ionization, and other this atmospheric pressure ionization and secondary ion mass spectrometry. Okay, so these are there. So how the mass is selected I have already discussed with you, so I am not going into the details of that one. Then we have a spectrometry where we call it as tandem mass spectrometry. Tandem means you are using one after the other. Okay, so you have the sample, you go for the ESI or the Maldi techniques for the ionization process, then you created the cations, you have one set of separation. So once you have this separation, then again you go for the fragmentation, and over here we go for the chemical ion dissociation or defragmentations. Okay, then again you go for the second stage of defragmentation, then you go for the separation again for the detection of the molecules. Now over here we use a word TOF, Maldi-TOF, in tandem mass spectrometry, Maldi-TOF, where TOF is the time of flight. Okay, TOF is the time of flight. Now what it does, as I told you, if you are having a larger fragment, it will be having a larger momentum and it will come out of the first analyzer, or the separation will happen. In that separation, the first what we will be getting, we will be getting the larger fragments. Then this larger fragments, it will be first getting into the MS2, that means the second mass spectrometer. As I told you, the fragments with larger masses, they will come out and they will again enter into the second mass spectrometer, and then accordingly you get the peaks. Okay, so in tandem mass spectrometry, you will be having two spectrometers which will be there, and one after the other. In the first stage you will be doing some analysis, and then again in the second stage you will be going for the further analysis. And why it is important in DNAs and all these things, and or the protein analysis, if you want to go for this kind of analysis, what happens is that in the first stage you are trying to understand what is the molecular mass of your protein, and in the second stage, why it is important? The second stage is important because you want to understand what are the amino acids which are present into the system. Okay, That's why this tandem mass spectrometry, it is very useful, and it is used in the biology. Okay. Then coming to the electrospray ionization. So in the electrospray ionization, what happens is that you have a solution of your proteins or the genetic materials. However, you choose the pH such that your molecules, they are ionized, either positively charged or negatively charged. Then you pump it out, and you create, through a nozzle, you create an aerosol. Now this aerosol, what are they? They are small droplets, but they are still liquid. Now you can apply an environment over here. So what will happen? A hot environment will be there where your solvent will be evaporated, but the process will not be very fast. So due to this reason, what it is done is that at the outlet of this syringe thing, or of this syringe, we apply a very high voltage, and when we are applying this high voltage, it is in the order of the 3 kilovolt. So when you are applying a very high voltage, what is happening? Basically, you are applying a thermal, you are applying a electric drag, and due to that electric drag, there is also a generation of the heat, and that heat which is being generated, that is resulting in the evaporation of the solvent. So it is promoting the evaporation of the solvent, and by the time, if you see, there is an annulus, these aerosols, they reach over here, we are getting the charged particles, and these charged particles, then they gain entry into the this analyzer section. Okay. Then Maldi matrix assisted laser desorption or ionization. So as I told you, we are having a laser. It is being high powered laser. It is used to ablate the sample which are being embedded within a matrix, and then it enters into the analyzer, and then it goes to the detector. Now CID. So CID is collision induced dissociation, which is used in the second stage of the tandem mass spectrometry. So over here you may have either homolytic fragmentation or heterolytic fragmentation. However, if you see the charged particles, they are being produced in the heterolytic fragmentation. So we are basically interested in the heterolytic fragmentation. Okay. With this, we complete this chapter. If you have any questions, we can discuss.